a faint point appeared beside Alpha Centauri A, more than 4 light-years away, in a place where the glare of the nearest sun-like star should have hidden almost everything. Webb detected it once in mid-infrared light, possibly a cold giant planet moving through a region that astronomers care about deeply. Then the telescope looked again, and the point was gone. Not confirmed as a planet, not dismissed as a mistake. It became something more careful and more interesting, a test of whether the nearest solar twin has been hiding a world in plain sight. A gentle like subscription or share helps calm space science continue creating calm, thoughtful, high-quality journeys through the universe. Thank you for spending your time watching. Please leave a comment with where you're watching or listening from, what time it is there, and whether this video is keeping you company while relaxing, studying, or settling down for sleep. The story now begins with a nearby star, a missing signal, and a question still waiting inside the glare. Alpha Centauri begins as a nearby point of light, but it does not remain simple for long. Its importance comes from a rare combination of distance, familiarity, and resistance. It is the nearest stellar system to the Sun, close enough that its light crosses interstellar space in only a little more than 4 years. Yet its inner structure has remained difficult to read with confidence. To unaided eyes beneath southern skies, it appears as one bright star. To astronomy, it is a compact neighborhood of 3 stars with different characters and different scientific meanings. That difference between appearance and reality is the first quiet lesson of the system. The closest place beyond the solar system is not automatically the easiest place to understand. It is close, bright, famous, and still incomplete. Alpha Centauri A is the star at the center of the present mystery. It is a solar-type star, similar enough to the Sun that it has long carried a special weight in planetary science. It is slightly larger and brighter than the Sun, but it belongs to the same broad family of stable hydrogen-burning stars. That makes it more than a bright object in the sky. It makes it a nearby example of the kind of star around which a familiar planetary system might, in principle, exist. A world receiving light from Alpha Centauri would not be orbiting a small red dwarf or an unstable young star. It would be orbiting a mature star with a broad resemblance to the one that has shaped Earth for billions of years. This doesn't mean such a world exists, and it doesn't mean that any planet there would be Earth-like. It means the question has always felt unusually direct. Around the nearest solar cousin, are there planets? And if there are, what kind of system have they made? Alpha Centauri B changes that question immediately. It is smaller and cooler than Alpha Centauri A, but still sun-like in a broader sense. The 2 stars are bound together by gravity and move around a shared center of mass in an orbit lasting nearly 80 years. Their separation changes as they travel along an elongated path. At times they are farther apart, and at other times they draw closer, altering the gravitational environment through which any planets must survive. This makes the system scientifically rich, but also difficult. A planet around Alpha Centauri A would not be forming or orbiting in isolation. It would exist inside a binary star system, where the companion star can shape the edges of stable orbits, disturb material in a young planet-forming disk, and complicate the interpretation of later observations. The system is not a clean copy of the solar system placed nearby. It is a different arrangement from the beginning, with 2 substantial stars sharing the same region of space. Far beyond the central pair is Proxima Centauri, the faint red dwarf that is technically the closest individual star to the Sun. Proxima is part of the larger Alpha Centauri system, but it is separated from Alpha Centauri A and B by a great distance, and moves on a very long orbit. It has already become famous for another reason. Planets have been detected around it, including at least one world in the broad region where liquid water could be possible under the right conditions. Yet Proxima is not the main focus of this story, because red dwarfs are very different from solar-type stars. Their habitable zones lie close to the star, and their activity can make nearby planets difficult places for stable atmospheres. Proxima matters deeply, but it does not answer the older and more specific question attached to Alpha Centauri A and B. The nearest red dwarf has shown that planets can exist next door. The nearest Sun-like pair has not yet given a confirmed planet at all. That absence is one of the most striking facts in modern exoplanet research. Thousands of planets have been found around stars scattered across the galaxy. Some were detected by the small dimming of a star as a planet passed in front of it. Others were inferred from the slight motion of a star pulled by an unseen companion. Many of these systems are much farther away than Alpha Centauri, and some are known in impressive detail despite their distance. Yet the central pair of the nearest star system remains without a confirmed planet. The result feels counterintuitive, but it follows from the practical limits of observation. Nearby does not always mean easy. Alpha Centauri A and B are bright, close to each other on the sky, and in constant mutual motion. Their light is valuable for studying the stars themselves, but that same light can overwhelm the faint signal of a planet. Their gravitational relationship also adds complexity to the search for tiny stellar motions caused by smaller bodies. The difficulty is not a lack of attention. Alpha Centauri has been watched with care for a long time. It has been a natural target for instruments designed to search for nearby worlds, and its importance has only grown as exoplanet science has matured. The system is often treated as the first serious destination beyond the solar system, both in technical proposals and in the wider imagination of interstellar travel. That cultural familiarity can make it seem more understood than it is. In practice, the scientific record is cautious. A claimed small planet around Alpha Centauri B once drew intense interest, but later analysis did not support it as a secure detection. Other possible hints have remained uncertain. The system has repeatedly produced the same pattern, enough importance to demand attention, enough difficulty to prevent a settled answer. This is why the recent attention from the James Webb Space Telescope matters so much. Webb did not look at a random star with a faint hope of finding something. It looked toward the nearest solar-type star, a target where the absence of confirmed planets has become part of the mystery. The telescope is powerful, but the challenge was not only to collect light. The challenge was to remove light, to suppress the glare of Alpha Centauri A and reduce the interference from Alpha Centauri B well enough to search for a much fainter object nearby. That is a demanding kind of astronomy. It does not produce an ordinary picture in which a planet simply stands beside a star. It requires careful separation of signal from glare, and it requires caution at every stage because faint points near bright stars can be created by several different effects. The first section of this story, therefore, cannot begin with a confirmed world. It begins with a system that should have been simple, and is not. Alpha Centauri is nearby enough to feel like the first external test of whether the solar neighbourhood contains familiar planetary architectures around sun-like stars. It is also complex enough to resist the tools used to study systems far beyond it. The central pair is bright, gravitationally linked, and observationally difficult. Proxima has planets, but it is a different kind of star and cannot settle the question of whether the solar-type stars have worlds of their own. Around Alpha Centauri A, the most important fact before Webb is not discovery but absence. Not an empty absence that proves there are no planets, but a measured absence created by limits in detection, uncertainty in past signals, and the strong light of the stars themselves. In that setting, any faint object detected near Alpha Centauri carries more meaning than its small appearance suggests. It is not only a possible planet, It is a test of whether the nearest Sun-like system has been hiding structure below the threshold of earlier searches. It also tests how carefully astronomy can work at the edge of its own instruments. The system has been familiar to human observers for centuries, but familiarity is not the same as knowledge. A bright point can be named, measured, and placed on charts while its planets remain unseen. A nearby star can become a symbol of future travel while its actual environment stays unresolved. Alpha Centauri is important because it lies close to the Sun, but its deeper value comes from the way it breaks a simple expectation. The closest Sun-like stars are not an open book. They're a difficult observing problem, a binary system with a faint outer companion, a history of uncertain planet claims, and a new set of questions sharpened by Webb. Before any faint point appears in the data, the stage is already scientifically unusual. The nearest solar twin is not waiting as a familiar copy of home. It is a nearby system with its own architecture, its own limits, and a blank space where confirmed planets around Alpha Centauri A and B still have not yet been placed. The difficulty around Alpha Centauri A begins with a simple imbalance. The star is bright enough to give astronomers detailed information about its own temperature, mass, light, and motion. Yet that same brightness makes nearby planets extremely hard to separate from the glare. A planet does not compete with its star on equal terms. Even a large planet reflects only a small amount of starlight, and in many cases its own heat is faint compared with the radiation pouring from the stellar surface. Around a more distant or dimmer star, this difficulty can already be severe. Around Alpha Centauri A, it becomes one of the central obstacles in the search. The system is close, but its closeness strengthens both the opportunity and the problem. More light reaches the telescope, which improves measurement of the star, but it also floods the region where a faint companion would appear. This is why brightness, usually a gift in astronomy, becomes a kind of veil. The planet may be physically near enough to study, but observationally it sits beside a source that overwhelms the field. Direct imaging has to deal with this imbalance first. It is not enough for a telescope to be large, sensitive, or placed above Earth's atmosphere. It must control the star's light with extraordinary precision. The light does not stay neatly inside the visible disk of the star. It spreads through the optical system, scatters from mirrors and structures, and produces patterns in the image that can resemble faint sources. A planet beside a star is not hidden only by brightness in a general sense. It is hidden by the behavior of a light inside the instrument. That makes the search both physical and technical. Astronomers must understand the star, the telescope, the detector, and the processing methods before they can decide whether a point in the image belongs to the sky or to the instrument. Alpha Centauri A makes this demand unusually strict because the possible planet signal is expected to be many thousands of times fainter than the star in the same observation. A small residual error can matter. A slight imperfection in the subtraction of glare can create an apparent feature. A real point can also be weakened or removed if the processing is too aggressive. The search, therefore, becomes a careful balance between revealing faint structure and not inventing it. Alpha Centauri B adds another layer to the problem. The companion star is not a faint background detail. It is a real sun-like star with its own strong light, and it lies close enough on the sky to interfere with observations of Alpha Centauri A. The two stars move around each other over nearly 80 years, so their apparent separation changes with time. For any observing campaign, the geometry of the pair matters. The light from Alpha Centauri B can enter the field, create additional patterns, and complicate the attempt to remove the glare from Alpha Centauri A. This means that the search for a faint planet near one star must also account for the other star. In a single star system, the dominant difficulty is usually the central star. In Alpha Centauri, the glare comes from a pair. The image is not simply a star with a possible planet next to it. It is a bright star, a bright companion, overlapping optical effects, and a faint region where the desired signal may be located. This is one reason older searchers struggled. Planet detection methods work best when the target behaves in a clean and predictable way. In the radial velocity method, astronomers measure tiny shifts in starlight caused by the motion of a star as an orbiting planet pulls on it. The method has found many planets, but it becomes difficult when the signal being sought is extremely small and the star is part of a binary. Alpha Centauri A and B already have a large mutual motion that must be modelled accurately. Only after that larger motion is understood can smaller planet-induced motions be searched for. Any remaining stellar activity, instrumental drift, or sampling pattern in the data can imitate a weak signal. The earlier claimed planet around Alpha Centauri B showed how fragile such detections can be. It first appeared to be a remarkable result, but later work did not support it as a secure planet. The lesson was not that planets are unlikely there. The lesson was that the system can produce signals that demand caution. A small pattern in the data is not enough when the target is this difficult. The transit method faces a different limitation. A planet has to cross the face of the star from Earth's point of view, and that alignment is uncommon for planets in wider orbits. A planet can be real, stable, and scientifically important without ever producing a transit. Around Alpha Centauri A, even a transit would be only a narrow kind of evidence. Useful if it happened, but unable to reveal everything that might be present. The method is excellent for systems aligned in the right way, but it cannot be treated as a complete census of nearby planets. A world may orbit outside the line of sight and leave no repeated dip in the star's brightness. For the nearest Sun-like system, the absence of such dips cannot close the question. It only means that one pathway to discovery has not produced a confirmed answer. Direct imaging is attractive because it does not require the planet to cross in front of the star. It tries to isolate the planet's own light or heat. For Alpha Centauri A, this is the method that brings Webb into the story. Webb observes in infrared wavelengths, where cooler objects can be more favourable targets than they are in visible light. A mature gas giant does not shine like a star, but it can emit thermal radiation. The mid-infrared range is especially useful for searching for colder planets, because it can reveal heat that reflected visible light would miss. This does not remove the star, Alpha Centauri. A remains bright in infrared light as well, but the contrast can become less unreachable, and that is enough to make a difficult search possible under carefully chosen conditions. The instrument used for this effort was Webb's mid-infrared instrument, often called MIRI. Its role was not merely to take a picture, it had to operate with a coronagraph, a device designed to block the central light of a bright star so fainter sources nearby can be searched for. A coronagraph does not make the star disappear. It reduces the strongest part of the glare and leaves behind a field that must still be interpreted with care. The blocked star continues to produce residual patterns. Light leaks around the mask and through the optical system. The remaining structure is not random, but it is complicated enough that the final image must be processed and compared against expectations. In this kind of observation, the image is not a direct view in the ordinary sense. It is the result of suppression, calibration, subtraction, and testing. Every step matters because the desired signal is faint and the surrounding light is strong. Webb also has limits imposed by geometry. A chronograph has an inner working region, a zone close to the star where faint objects cannot be separated reliably from the leftover glare. A planet may be outside this region during one part of its orbit and inside it during another. This matters especially for Alpha Centauri A because the region of interest lies close to the star in angular terms. The system is nearby, So a planet at a few times Earth's distance from the Sun is more widely separated on the sky than it would be around a distant star, but the separation is still small. The possible signal has to appear outside the worst residual glare while remaining faint enough to test the instrument's sensitivity. This makes timing important. A real planet may be visible during one observing window and hidden during another, depending on where it lies in its orbit and how the system is angled relative to Earth. The brightness problem therefore shapes the entire mystery before any candidate is evaluated. It explains why Alpha Centauri A can be one of the most studied nearby stars and still lack a confirmed planet. It explains why a faint point in the data cannot be accepted too quickly. It also explains why such a point, if it survives the first checks, is so important. The search is not being conducted in a quiet field with an isolated object. It is being conducted beside one of the brightest stellar targets available, with another bright star nearby, using an instrument pushed into a demanding mode of observation. A detection under those conditions would not be routine. It would show that the glare can be reduced enough to reach a new level of sensitivity around the nearest solar-type star. At the same time, it would require more evidence than a single appearance, because the same conditions that make the discovery valuable also make false signals possible. Alpha Centauri A is not hard to study because it is remote. It is hard to study because the very light that reveals the star conceals what may be orbiting close to it. Alpha Centauri A became a different kind of target when Webb observed it in the mid-infrared. The star was not being examined only for its own properties, which were already well studied. It was being used as a test of whether a telescope designed for faint heat and careful contrast could separate something much dimmer from the light of the nearest solar-type star. In August 2024, Webb's mid-infrared instrument looked toward Alpha Centauri A with a coronagraph in place, suppressing the star's central glare so that the region around it could be searched for a faint companion. The observation did not begin with a visible planet waiting in a clean field. It began with a bright star, a nearby bright companion, and a detector filled with residual structure. Only after careful processing could the search move into the narrow space where a planet, dust feature, or artifact might appear. That distinction matters because the result was not a photograph in the ordinary sense. It was a difficult extraction from a complicated field of light. Webb had to block much of Alpha Centauri A, account for the influence of Alpha Centauri B, and search the remaining image for a compact source that stayed meaningful after the most obvious false explanations were considered. The work depended on the mid-infrared because a cool giant planet is not best found by reflected visible light. It is more likely to reveal itself by its own thermal emission, a faint warmth left from formation and maintained by the physics of a massive atmosphere. Such a planet would still be much dimmer than the star, but in these wavelengths the contrast becomes less severe than it would be in visible light. The observation was therefore aimed at a difficult but realistic possibility, not an Earth-like world. Not a small, rocky body, but a larger and colder object whose heat might be just strong enough to separate from the glare after the glare was reduced and the image processed. A faint point source appeared near Alpha Centauri A. Its importance came from both its weakness and its location. It was not a bright object that forced an immediate conclusion. It was a small signal, more than 10,000 times dimmer than the star in the relevant infrared observation, and it existed close enough to the star that the measurement had to be treated with great caution. Yet it was not located in a random part of the field. It appeared at a projected separation consistent with the region where a giant planet could orbit the star. On the scale of the system, that placed it in an area of strong interest, close enough to raise questions about planetary architecture rather than only distant debris. The source could not be turned into a planet simply because it was tempting. A responsible interpretation had to begin with doubt. The first question was whether the point was a background object unrelated to Alpha Centauri. A distant star or galaxy can line up by chance near a nearby star, and astronomical images are always layered in this way. Alpha Centauri's own motion across the sky helps with this kind of test because the system shifts against the far background over time. The candidate did not immediately fit the simplest background explanation, but that alone was not enough. The next question was whether it could be an object inside the solar system, a small body passing through the field at the moment of observation. That possibility also had to be weighed against expected motion, position, and brightness. It did not provide an easy dismissal. The harder question remained the instrument itself. Webb is extremely stable and sensitive, but it is still an optical system. The coronagraph does not remove every trace of the star. It changes the shape of the problem by leaving residual light that must be understood. Patterns from diffraction, scattered light, detector behavior, and subtraction can produce compact features that resemble faint sources. Around a bright target like Alpha Centauri A, this possibility cannot be treated as an afterthought. A source that appears after complex processing must be tested not only against the sky, but against the ways the instrument can shape the image. This is why the observation was described as a candidate rather than a confirmed discovery. The word candidate is important. It signals that the point is neither ignored nor accepted. It is a scientific possibility strong enough to deserve follow-up, but not strong enough to stand alone. The behavior of the source made the situation more interesting. It survived enough of the first checks to remain in the discussion. It was not obviously a known background source, not easily explained as a passing local object, and not immediately dismissed as a simple processing error. Its brightness was also broadly consistent with what might be expected from a cold giant planet under certain assumptions. That did not fix its mass or nature. Planet brightness in the mid-infrared depends on age, temperature, atmosphere, radius, and model choices. A measured glow does not translate into a single clean answer. Still, the signal fell within the range where a Saturn-like or Jupiter-like planet became a plausible interpretation. This mattered because such planets have been difficult to image around mature Sun-like stars at relatively small separations. Most directly imaged exoplanets are young, warm, massive, and far from their stars, which makes them easier to see. A colder giant near Alpha Centauri A would belong to a more demanding class of target. The possible location of the source gave it additional weight. It appeared near the broad region often discussed in relation to habitability, though this phrase requires careful restraint. The habitable zone is not a guarantee of life. It is the distance range where a rocky planet with suitable atmospheric conditions might support liquid water on its surface. A gas giant in that region would not be habitable in the same way. It would not offer solid ground or a surface ocean like Earth, but its presence would still matter. A giant planet there would shape the system around it through gravity. It could influence debris, affect the stability of smaller planets, or record a history of migration and interaction. The discovery would not be important because it revealed a second Earth. It would be important because it would show that Alpha Centauri A has significant planetary structure in a region where previous searches had left the system unresolved. The observation also changed the emotional scale of the nearby star without changing the scientific caution. Before Webb, Alpha Centauri A could be described as a star with no confirmed planets. After the August observation, it remained a star with no confirmed planets. But the absence had become less simple. The data now contained a specific faint source that required explanation. It could become a planet with future confirmation, or it could become a well-studied false signal that improves the methods used for similar searches. In either case, the result marked a boundary. Webb had reached close enough to the star and deep enough into the mid-infrared contrast problem to produce a serious candidate around the nearest solar-type star. That achievement alone showed how exoplanet searches are entering a more delicate stage. The question is no longer only whether planets can be found around distant systems through indirect methods. It is whether faint planetary light can be isolated near the stars most important for comparison with the Sun. Yet the first glimpse did not settle the issue. One observation cannot establish an orbit. It cannot prove that a source shares the motion of Alpha Centauri A, follows a gravitational path around the star, or persists when the telescope looks again. Direct imaging needs repetition because planets move predictably, while artifacts and chance alignments do not have to obey the same pattern. The August signal therefore opened a test rather than ending one. It gave astronomers a position, a brightness, and a set of possible interpretations. It also gave them a demand look again, and see whether the source behaves like a body in orbit. That demand is what gives the glimpse its importance. The faint point was not a final answer beside Alpha Centauri A. It was the first piece of evidence in a narrow and difficult case. The nearest solar-type star had not suddenly become known. It had become more complicated in a precise way, because Webb had shown that something at the edge of detection could appear where a planet might be, and the next question was whether that point belonged to the system or only to the glare. Alpha Centauri A did not keep the faint point in view. After the August 2024 observation, the scientific need was direct and unavoidable. Webb had to look again. A real planet should not remain fixed in one place, because it would be moving around the star under gravity. A background object would follow a different apparent path as Alpha Centauri shifted against the far sky. An artifact might not repeat at all. The follow-up observations were therefore not routine checks. They were the first attempt to decide whether the signal had a physical life beyond a single image. When Webb returned in February 2025, the point source was not recovered. When the telescope observed again in April 2025, it was still absent. The same system, the same central star, and the same broad observing goal now produced a different result. The candidate that had made Alpha Centauri feel newly active was no longer visible. In many areas of astronomy, a non-detection can sound like an ending. If a source appears once and then cannot be found again, the simplest suspicion is that the first signal may not have been real. Around a bright star observed with a coronagraph, that suspicion is necessary. The process of suppressing starlight can leave structures that are difficult to remove completely. A small residual feature can appear stronger in one reduction than in another. Detector effects, imperfect subtraction, or the changing glare from the companion star can produce a compact source that looks more meaningful than it is. Scientific caution therefore had to move ahead of excitement. The later images did not confirm a planet. They removed any responsible path toward a quick announcement. The object could not be treated as an established world around the nearest solar-type star. It had appeared once, and a single appearance is not enough. But the disappearance was not a simple rejection either. The geometry of direct imaging allows a real planet to become hidden without ceasing to exist. A planet orbiting close enough to Alpha Centauri A would change its apparent separation from the star as it moved along its path. At one point in the orbit, it could sit far enough from the star's apparent position to be separated from the remaining glare. At another point, it could move closer to the line of sight and fall inside the region where the coronagraph cannot reliably distinguish faint companions from residual starlight. This region is not empty space. It is an observational boundary. Objects inside it may still be present, but the image no longer has the contrast needed to identify them. The later non-detections therefore created a narrower question. They did not ask only whether the candidate was real. They asked whether a real planet, moving on a plausible orbit, could have been visible in August and hidden during the later visits. To answer that, Astronomers had to turn the single point into a family of possible paths. Each path had to be consistent with the first detection and with the mass of Alpha Centauri A. Each also had to respect the influence of Alpha Centauri B, because the companion star helps define which orbits around Alpha Centauri A can remain stable over long times. Some paths would keep a planet visible during the later observations, and those paths became less likely when Webb saw nothing. Other paths would carry the candidate into a zone too close to the stellar glare, and those paths remained viable. This is where the meaning of the missing point becomes more subtle. Non-detection is not the same thing as absence. It is the absence of a source under a specific observing condition, at a specific time, with a specific instrument and processing method. In a simple case, repeated non-detections can quickly weaken a claim. In this case, the possible motion of the object matters as much as its brightness. A faint companion near the inner limits of Webb's coronagraph could pass in and out of detectability. It could leave one measurable signal and then become inaccessible until the orbit carries it outward again in projection. This does not prove the planet interpretation. It only prevents the later observations from closing the case. The candidate remains balanced between two disciplined possibilities. It may have been a real body whose orbit placed it beyond Webb's reach during the follow-ups, or it may have been a false feature that naturally failed to repeat. Both interpretations require restraint. A real planet cannot be claimed without recovery. A false signal cannot be declared without explaining why the first source passed enough tests to remain interesting. The result is a scientific tension, not a dramatic event. It is a limited set of evidence that has to be treated according to what the instrument can and cannot show. The phrase disappearing planet can make the situation sound more mysterious than it is. Nothing in the data suggests that a physical world would vanish from space. The disappearance belongs to observation. If the source is a planet, it is still following an orbit around Alpha Centauri A. It may be lost in glare from Earth's perspective, where the star's light and the telescope's inner working angle prevent detection. If the source is not a planet, then the disappearance is a warning about how convincing a single processed point can be near a bright star. In both cases, the event exposes the difficulty of the target rather than any strange behaviour of the object itself. The nearest solar-type star has not offered a clean answer because the conditions for seeing faint companions there are severe. The later Webb images also force a careful distinction between a failed confirmation and a failed hypothesis. A failed confirmation means the evidence has not reached the level required to name a planet. That is clearly true. A failed hypothesis would mean the planet explanation no longer fits the evidence. That is less clear, because some orbital models can accommodate the missing source. The difference matters. Science does not move only through yes or no. Often it moves through changing probability, narrowing conditions, and removing the easiest versions of an idea while leaving more specific versions still alive. The Alpha Centauri candidate is now less simple than it was after the first observation. It can no longer be described as merely a faint point that appeared where a planet might be. It must also be described as a point that did not appear when Webb returned, and any planetary explanation must account for both facts together. That makes the next recovery attempt more demanding. If the candidate is real, future observations should not search blindly. They should be guided by the range of orbits still allowed. The source should reappear only when its projected separation from Alpha Centauri A becomes large enough for the telescope to detect it again. Its position should be consistent with orbital motion, not with a random point in the processed field. Its brightness should also remain plausible for a cool giant planet, allowing for changes in viewing geometry and model uncertainty. This is how a candidate becomes a discovery. It is not enough for a source to be interesting. It has to return in a way that matches gravity. Until that happens, The strongest claim is that Webb has produced a serious but unconfirmed signal around a star where Sirius signals are rare. The absence in February and April does not erase the August point. It changes how the point must be interpreted. It removes the simplest excitement and replaces it with a stricter test. This is a useful outcome even without confirmation. Because the search for nearby planets depends on learning how close to the glare instruments can be trusted, Alpha Centauri A is an especially valuable test because it is close, bright, and scientifically important. A false candidate there would still teach astronomers about coronagraphic imaging, background rejection, and the behavior of residual starlight near a difficult binary. A real candidate there would become one of the most important nearby exoplanet discoveries ever made. The current evidence sits between those outcomes. The star has not yielded a planet, but it has also not returned to the simpler blankness it had before. The vanishing signal is therefore best understood as a test of patience. Webb saw a faint source once near Alpha Centauri A, then did not see it again during 2 later visits. That pattern is exactly why the case cannot be simplified. The source may have moved into the glare, following an orbit that future observations can test. It may also have been created by the observational process itself, visible only under one set of conditions. The responsible conclusion is not that a planet has been found, and not that the possibility has disappeared. The conclusion is that the nearest solar-type star now contains a specific unresolved target, one that will either return under the discipline of orbital motion or fade into the record as a lesson in how hard it is to see faint worlds beside bright stars. The case for the faint source near Alpha Centauri A depends on eliminating easier explanations before giving weight to the difficult one. This is the discipline that protects a candidate from becoming a premature discovery. A point in a processed image can look simple, but it enters the scientific record only after passing through a series of questions. Does it belong to the Alpha Centauri system, or does it merely lie in the same direction from Earth? Does it move like an object bound to the star, or like something distant behind it? Could it be a small body inside the solar system passing across the field? Could it be warm dust shaped into a compact feature? Could it be produced by the telescope, the coronagraph, or the mathematical steps used to remove the star's glare? Each possibility has to be considered because the signal is faint, the star is bright, and the observation sits close to the limit of what the instrument can separate. The most direct interpretation is a planet. But it is not the first conclusion science is allowed to keep. It is one explanation among several, and it has to earn its place by surviving them. A background source is one of the first alternatives. The sky behind Alpha Centauri is not empty. Any telescope pointed at the nearest star system also sees through a much deeper field of stars and galaxies. A small dot near Alpha Centauri A could therefore be unrelated, a distant object that happens to line up with the star from Earth's perspective. In many observations, this is a serious risk. A faint star far behind the system can appear close to a nearby target on the image, even though the two objects are separated by enormous distance. Alpha Centauri provides a useful way to test this because it moves across the sky relatively quickly compared with distant background objects. Its nearness means its position changes measurably against the far stellar pattern over time. If a faint dot stays fixed while Alpha Centauri shifts, then it is probably not part of the system. If it shares the system's motion or appears in a place consistent with orbital movement around Alpha Centauri A, then the background explanation weakens. The August source did not reduce neatly to a known background object, which is one reason it remained interesting. But this does not make it a planet. It only removes one of the simpler exits. Another possibility is an object much closer to home. The solar system contains asteroids, comets, and many smaller bodies moving across the sky. Some are known and tracked, while many faint ones remain difficult to catalogue completely. A small solar system object could in principle pass through the field during an observation and appear as a point near Alpha Centauri A. This kind of explanation is less dramatic than a planet around another star, but it must be tested because it would produce a real source of light in the image without belonging to Alpha Centauri. Its apparent motion, likely brightness, and position have to fit the observing circumstances. For the Webb candidate, a local object did not provide a simple or favoured explanation, but again the important word is simple. Scientific rejection is rarely absolute at the beginning. It usually means that one explanation becomes less natural than another after the evidence is compared against expected behaviour. A third possibility is dust around Alpha Centauri A. Dust may sound minor, but in planetary systems it can be physically meaningful. It can come from collisions among asteroids, fragments shed by comets, or the long grinding of small bodies into fine grains. Warm dust can glow in infrared light, the same range used to search for cool planets. If dust is distributed unevenly, or if the processing of the image sharpens part of a broader structure, it can resemble a compact source. This matters because a dust explanation would still tell scientists that the system is active or structured, but it would not provide a planet with a clear orbit and mass. Dust does not behave like a single body. It can be shaped by radiation, collisions, and gravitational effects, and its appearance may change depending on wavelength and processing. A dust clump can imitate some properties of a planet while failing the stricter test of orbital persistence. This is why future observations are so important. A planet should return to a location allowed by gravity. Dust may not provide the same clean pattern. The most difficult alternative is an instrumental or processing artifact. This possibility cannot be dismissed simply because the telescope is powerful. Powerful instruments are still instruments, and every instrument has limits. Webb's coronagraph blocks much of the central light from Alpha Centauri A, but the suppression is not perfect. Residual starlight remains. It forms patterns shaped by the optical system, the mask, the detector, and the exact conditions of the observation. Then the data must be processed to remove the remaining glare and compare the target against references. These steps are necessary, but they also create risk. A feature can appear when subtraction is imperfect. A real object can be weakened if the processing treats it as part of the glare. A false compact point can survive some checks and fail others. This is why the candidate cannot be judged by appearance alone. The question is not whether the point looks like a source. The question is whether it behaves like one under independent tests. Around Alpha Centauri A, the risk of artifacts is heightened by the brightness of the star and by the presence of Alpha Centauri B. Light from the companion star complicates the field and changes the residual patterns that need to be removed. The system does not offer the clean conditions that make direct imaging easier. The detection, therefore, has to be treated as a product of both sky and instrument, until repeated observation can separate them. If the source is real and bound to Alpha Centauri A, it should have a path. If it is an artifact, it may be tied instead to the observing setup, the star's glare, or the processing method. The later non-detections do not settle the question, but they increase the need for this distinction. A feature that appears once and does not return is exactly the kind of evidence that demands further testing before it can be named. The planet interpretation remains the most compelling because of the source's position and brightness. If it is a world, it is unlikely to be small and rocky. It would more plausibly be a cool giant, perhaps in the broad class of Saturn-like or Jupiter-like planets, massive enough to emit detectable mid-infrared radiation. Such a planet would be important even without being Earth-like. It would show that Alpha Centauri A has a major planetary body in a region where gravitational influence could shape the system. It could affect debris belts, smaller planets, and the long-term stability of nearby orbits. It would also demonstrate that direct imaging can reach colder and less widely separated planets than many previous discoveries. That would make the detection a technical milestone as well as a local one. But the strength of that implication is exactly why the standard of evidence must stay high. The more important the discovery would be, the more carefully it has to be separated from false positives. The candidate has not yet made that crossing. It remains in a narrow scientific category where evidence is suggestive but incomplete. This category is not a failure. It is a normal part of searching at the edge of sensitivity. Many real discoveries begin as candidates. Many candidates later disappear because better data reveal artifacts, noise, or unrelated sources. What matters is not whether the first interpretation is exciting, but whether the signal can be made consistent across time, wavelength, and method. Alpha Centauri A now has a specific point of interest that future observations can test. The alternatives are clear enough to guide those tests. A background object should show the wrong motion. A solar system object should not remain tied to the star. Dust should lack the simple persistence of a single orbiting body. An artifact should fail to behave independently of the instrument and processing. A planet should return according to gravity. That is the structure of the case. The uncertainty around the Webb source is therefore not vague. It is organized uncertainty, divided into explanations that can be weakened or strengthened by further data. This is what makes the candidate valuable even before confirmation. It has forced Alpha Centauri A into a more precise scientific question. Not simply whether planets exist there, but whether this particular faint source is a world, dust, a distant alignment, a nearby interloper, or an artifact of observation. Each answer would mean something different. A planet would reveal a hidden architecture around the nearest solar-type star. Dust would point toward active debris and unseen small bodies. A background or local object would refine the interpretation of a difficult field. An artifact would improve understanding of how Webb behaves near one of the brightest and most demanding targets it has examined in this way. The system has not become less interesting because the answer is uncertain. It has become more clearly testable. The faint point near Alpha Centauri A is now evidence on the edge of several explanations, and only repeated, well-timed observation can decide which one survives. The Webb candidate did not appear in an empty history. Several years before the August observation, Alpha Centauri A had already produced a weaker and unresolved clue from the ground. That earlier signal came from a dedicated search using the Very Large Telescope in Chile, where astronomers tried to look into the warm infrared region around the nearest Sun-like pair. The effort was technically demanding for reasons that Webb later made clear in a different form. Alpha Centauri A is bright. Alpha Centauri B is close enough to interfere, and any planet in the region of interest would be far dimmer than either star. From Earth, another problem is added. The atmosphere is always moving, even at excellent observatory sites. Adaptive optics can correct some of that motion, and careful observing can reduce its effect. But the telescope is still looking through air. The search therefore required not only a powerful mirror, but a specialized instrument and careful processing designed to separate faint thermal emission from glare, atmospheric noise, and instrumental structure. The result was a possible source known as C1. The label was plain, but the location was not. C1 appeared near Alpha Centauri A in a region where a planet could plausibly exist. It was not presented as a confirmed world. It was a candidate, a faint excess in processed data that had several possible explanations. Its brightness and separation were compatible with a planet larger than Earth, perhaps in a range closer to Neptune or Saturn, depending on assumptions about temperature and age. But it could also have been dust, an artifact, or some other feature created by the difficulty of subtracting the star's light. The signal did not carry enough evidence to define an orbit. it did not return in a way that made its motion undeniable. It remained suspended, scientifically interesting but unfinished. That kind of result can be easy to overlook beside a major space telescope observation, but difficult discoveries often form through accumulation. One uncertain point is weak. A second uncertain point, measured with a different instrument years later, can begin to change the question, not by confirming the first, but by asking whether both belong to the same underlying structure. When Webb saw its own faint source near Alpha Centauri A, the resemblance to the older C1 candidate became one of the important parts of the story. The two observations were not identical. They came from different telescopes, different observing environments, and different technical limits. Each observation had its own ways of being fooled, yet both pointed toward the same star and suggested something faint where a giant planet or warm debris could plausibly appear. That was enough to raise a precise question. Could C1 and the Webb source be two appearances of the same object at different points in time? This question cannot be answered by resemblance alone. Planetary motion is constrained by gravity, and gravity gives the test its discipline. If 2 points seen years apart are to represent the same planet, a plausible orbit must connect them. That orbit has to pass near the position of the older source at the time it was observed, then near the position of the Webb source years later, while remaining stable around Alpha Centauri A. It also has to respect the gravitational influence of Alpha Centauri B, because the companion star limits which orbits can survive over long periods. The task is to ask whether a real body could have moved from one apparent location to the other, under the known mass and geometry of the system. In that sense, the older clue becomes a serious constraint rather than a coincidence. If the same object can explain both appearances, then the candidate becomes more interesting. If no reasonable orbit can connect them, then the similarity loses much of its force. The possible connection is especially important because direct imaging often struggles with single epoch detections. A planet must be followed over time to show that it belongs to the star. When only one point exists, the interpretation remains fragile. A second point can begin to reveal motion, but only if the positions and timing fit. The older C1 signal therefore acts like a possible earlier measurement of the same hidden companion. It does not prove the companion, because C1 itself was uncertain, but it gives orbital modelling a longer baseline. Instead of asking what paths could match the Webb point alone, scientists can ask what paths could match both the older ground-based signal and the newer space-based source. A longer time span can remove many possibilities and strengthen a few others. It can also expose contradictions. If the candidate is real, its past and present locations should not be random. They should fall along a path that belongs to a body orbiting Alpha Centauri A. The outcome of that comparison remains cautious. The connection between C1 and the Webb source is plausible enough to be taken seriously, but not strong enough to settle the case. Some possible orbits can link the two signals while also explaining why Webb did not recover the source during later observations. In those models, the object could have moved into the inner glare, then later might emerge again at a separation that instruments can test. Other possibilities remain open. C1 may have been an unrelated artifact from ground-based processing, while the Webb source could be a different artifact, a dust feature, or a real object. The fact that two uncertain observations can be connected does not make certainty. It makes a testable hypothesis. The scientific value lies in the way the hypothesis can be checked. A future detection should appear not merely somewhere near Alpha Centauri A, but near a location predicted by the orbit that links the older and newer clues. That is the standard the evidence must meet. If the possible object reappears according to one of the allowed paths, the older C1 observation will become much more important. It may be reinterpreted as the first faint glimpse of the same planet before Webb saw it. If the object fails to return, then C1 may remain what it has been for years, an unresolved feature from a difficult search. This reflects the nature of observing at the boundary of sensitivity. The search for planets around Alpha Centauri A is difficult enough that even well-designed observations can produce candidates that cannot be fully judged without later evidence. In this field, uncertainty is not a flaw in the method. It is the condition under which the method operates. What makes C1 valuable is that it provides a specific earlier clue rather than a general hope. It gives scientists a recorded position, brightness estimate, and observing context to compare with Webb's source. The comparison also deepens the larger picture of Alpha Centauri A. If both signals are related, then the system may have been showing signs of a planet for years without allowing confirmation. That would mean the difficulty is not the absence of all evidence, but the incompleteness of each piece. The star would not be blank. It would be partially legible. Signals would appear at the edge of what instruments can see, then disappear into glare, noise, or unfavorable geometry. This is a more complicated situation than either discovery or non-discovery. It suggests that the nearest Sun-like star may require a long record of carefully timed observations before its planetary structure can be separated from false positives. A confirmed connection would also change how the possible planet is understood. It would imply an orbit with enough movement over the intervening years to match two widely separated observing dates. Depending on the final orbital solution, the planet might follow a path that is more stretched than a simple circle. It could move closer to Alpha Centauri A at one part of its orbit and farther away at another, changing both its physical distance from the star and its apparent separation in the sky. Such a path would help explain the pattern of detection and non-detection. It would also raise questions about how a giant planet reached or maintained that orbit inside a binary system. The older clue, therefore, points forward into the next layer of the mystery. It is not only a possible match to Webb's point, it is a doorway into orbital history, system stability, and planet formation under the influence of two stars. For now, C1 remains a clue with limited authority. It cannot confirm Webb's candidate, and Webb's candidate cannot rescue C1 from uncertainty by resemblance alone. But together they define a clearer problem than either signal could create independently. Somewhere near Alpha Centauri A, two difficult observations have found faint structure that may or may not belong to the same body. The only way to resolve that structure is to let time and gravity continue the test. If the source returns where a connected orbit predicts, the older ground base point will no longer look isolated. It will become part of a longer track. If it does not, both signals may remain separate warnings about glare near a bright star. The older C1 clue, therefore, does not close the case. It gives the case a past, and that past makes the next observation more meaningful. Alpha Centauri, he now has a problem that cannot be solved by appearance alone. The faint source seen by Webb and the older C1 signal from the ground only become physically meaningful if they can be placed onto a possible orbit. This is where the search leaves the image and becomes a calculation about motion. A planet is not a fixed dot beside a star. It is a body following a path controlled mainly by gravity, and that path limits where it can be at different times. If a source appears near Alpha Centauri A in 1 year, then appears elsewhere several years later, the two positions cannot be joined freely. They must be connected by a path that a real body could travel around a star of Alpha Centauri A's mass. The question is not simply whether the two detections look similar. The question is whether one object could move between them without breaking the rules that govern orbital motion. That makes gravity the strongest test available before the candidate is seen again. The first step is to translate each observation into a position relative to the star. This is more difficult than it may sound, because the image gives only a projected position on the sky. It shows where the source appears from Earth, not its full location in three-dimensional space. a planet may be closer to or farther from the observer along the line of sight, and that depth is usually unknown. The observed separation is therefore not the complete distance from the star. It is a shadow of the orbit on the sky. Because of that missing depth, many different orbits can pass through the same apparent point. Some may be nearly circular, some may be elongated, some may be tilted toward Earth, while others lie closer to the plane of the sky. A single detection leaves this family of possibilities wide open. Adding C1 gives the problem another anchor, but it does not remove the uncertainty completely. It narrows the family of possible paths if the 2 points are truly connected. To test that connection, scientists can generate many possible orbits and ask which ones satisfy all the known constraints. Each orbit has a size, a shape, a tilt, and a timing. The size describes how far the planet ranges from the star. The shape describes whether the path is close to circular or stretched into an ellipse. The tilt describes how the orbit is angled relative to Earth. The timing describes where the planet would have been at the moments of the older and newer observations. An orbit that fits the older C1 position but misses the Webb point cannot explain both. An orbit that fits Webb but requires the object to move too quickly or too slowly for its distance also fails. An orbit that would have placed the object clearly in view during the February and April follow-ups becomes less likely because Webb did not recover it. The useful orbits are the ones that allow the source to appear when it was seen and become hidden when it was not. This is a demanding but valuable filter. It turns non-detections into information. The missing source in later observations is not simply blank space. It tells scientists which orbital paths are less compatible with the data. If a possible planet would have been well outside the inner glare of the coronagraph during those observations, and if it should have been bright enough to see, then that orbit becomes harder to keep. If another orbit places the planet too close to the star's apparent position during the same observations, then the non-detections are easier to understand. In this way, the absence of the point can help shape the range of possible motion. It does not prove that the source exists, but it prevents all possibilities from being treated equally. The system's geometry gives the case structure. Alpha Centauri B adds another constraint. A planet around Alpha Centauri A is not orbiting in a single star system like the Solar System. It is orbiting one member of a binary, and the companion star changes the long-term stability of possible paths. Orbits too wide around Alpha Centauri may be disturbed by Alpha Centauri B over time. Orbits with certain shapes may become unstable if the companion's pull repeatedly changes their orientation or distance. A possible giant planet must therefore occupy a path that can survive not only for the few years between observations, but for much longer periods if it is truly part of the system. Stability does not prove the planet is real, but instability can rule out some interpretations. A path that connects the observed positions but could not remain intact in the binary environment is not a satisfying explanation. The orbit must fit both the short-term evidence and the long-term setting. This is why a possible connection between Webb's candidate and C1 is scientifically delicate. The 2 points may be linked by some plausible orbits, but those orbits must be tested for more than geometry. They need to make sense dynamically. They need to keep the object bound to Alpha Centauri A rather than placing it on a path that would be disrupted or ejected. They need to be consistent with the expected range of brightness for a cool giant planet, because orbital distance affects the amount of starlight received and can influence the temperature estimate. They must also allow the object to move into and out of detectability in a way that matches the actual observing windows. The best models are not the ones that make the most exciting claim. They are the ones that explain the most evidence with the fewest unsupported assumptions. If the candidate is real, the orbit may be more elongated than a simple circular path. That possibility matters because it could explain why the source appears near the limits of detection at some times and vanishes at others. On an elongated orbit, the planet's distance from Alpha Centauri A changes over its year. Its apparent separation on the sky also changes as the orbit carries it through different positions relative to Earth. A planet on such a path may spend part of its time easier to separate from the star and part of its time buried near the inner working region of the coronagraph. This would not be unusual behavior for a planet in general, but it would be especially important for a difficult target like Alpha Centauri A. The instrument does not have equal access to every part of the orbit. Visibility depends on where the planet is, how bright it is, and how far from the star it appears at that moment. The modelling also helps separate a planet from less disciplined explanations. A background object does not share an orbit around Alpha Centauri A. A solar system object does not remain tied to the star over multiple years. A dust feature may follow broad orbital behaviour if it belongs to a debris structure, but it is less likely to behave as a single compact body returning to precise predicted positions. An artifact has no reason to follow any path controlled by the star's gravity. This is why the next useful observation is not just another search for a faint dot. It is a test of prediction. If an allowed orbit says the candidate should emerge from the glare in a particular region at a particular time, then an observation can look there with purpose. A recovery at the predicted position would strengthen the planetary interpretation far more than another isolated point elsewhere. Failure to recover the source when the models say it should be visible would weaken the case. That future test gives the present uncertainty a clear direction. The candidate is not a vague mystery waiting for better luck. It is now tied to a set of possible paths that can be checked. The older C1 clue, the August Webb source, and the later non-detections together form a limited but useful record. The record is incomplete, and it may still point toward a false signal, but it is structured enough to guide the next observations. This is the main value of orbital modelling. It does not replace observation. It tells observation where and when to matter most. For Alpha Centauri A, the calculation is especially important because direct imaging near the star is expensive in observing time and difficult in execution. A well-timed look can test the stronger surviving versions of the planet hypothesis, while a poorly timed one may only repeat the ambiguity. The result is a slower form of discovery than a single clear image, but it is also more reliable. A true planet should not only appear, it should move with consistency. It should pass through positions that connect past and future observations. It should remain compatible with a stable orbit in the presence of Alpha Centauri B. It should be visible when the models say the glare no longer hides it, and absent when the geometry makes detection unlikely. Until that pattern is seen, the object remains a candidate, but the uncertainty has become more exact. Gravity has reduced the question from whether a faint point looked interesting to whether one body can account for a sequence of appearances and absences around the nearest solar-type star. Alpha Centauri A draws attention because it resembles the Sun, but the possible Webb source would not resemble Earth. If the faint point is a planet, its mid-infrared brightness points toward a larger and colder body, more consistent with a gas giant than with a small rocky world. That distinction is essential. A giant planet in or near the broad habitable zone of a solar-type star is not automatically a habitable planet. It would not have a solid surface like Earth, and its visible upper layers would be atmosphere, cloud, pressure, and heat moving through deep gas rather than continents or oceans. The scientific importance would come from structure, not from immediate habitability. A large planet in this region would show that Alpha Centauri A is not a bare star with empty space around it. It would show that at least one substantial body formed, survived, or migrated into a part of the system where earlier searches had not confirmed anything at all. The habitable zone is often misunderstood because the phrase sounds more definite than it is. It describes a range of distances from a star where a rocky planet, with the right atmosphere could maintain liquid water on its surface. It is not a statement that life exists there. It is not even a statement that any planet in that region has suitable conditions. Venus, Earth, and Mars show why caution is necessary. They receive different amounts of sunlight and have very different atmospheres, and their histories did not lead to the same outcome. A planet's place near the right temperature range is only one part of a larger problem involving air, water, geology, magnetic fields, impacts, chemistry, and time. Around Alpha Centauri A, the possible object would add another layer to that caution. If it is a gas giant, then the object itself is not the kind of world usually meant by a habitable zone planet. It would be important because of what its gravity may imply for the rest of the system. A gas giant can be a major force in planetary architecture. Its mass can shape the paths of smaller bodies, influence debris belts, and change which orbits remain stable. In the solar system, Jupiter and Saturn are not simply distant large planets. Their gravity has affected the asteroid belt, the distribution of small bodies, and the long history of impacts and migration. Around Alpha Centauri A, a comparable giant would have similar importance, even if its details were very different. It could clear regions of smaller material, trap objects in resonant orbits, scatter icy bodies, or help preserve stable zones elsewhere. Its presence could make some orbits safer and others less stable. It could also reveal that the system went through a more active early history than the absence of confirmed planets had suggested. A giant world is therefore not only a world, it is evidence that the system has been organized by gravity on a planetary scale. This matters because Alpha Centauri A has long been treated as the most natural place to compare with the Sun. A simple expectation would place small rocky worlds close to the star and larger planets farther out, because that is the broad arrangement familiar from the solar system. But exoplanet science has already shown that this pattern is not universal. Many systems contain large planets close to their stars, compact groups of super-Earths, eccentric giants, or planets moving in configurations that would have seemed unusual before the first discoveries. If Alpha Centauri A has a giant planet near the region of temperate starlight, then the nearest solar-type star would not be following the most familiar version of solar system architecture. It would be nearby, but not necessarily similar. That would be an important correction to expectation. Proximity can make a system feel familiar before its actual arrangement is known. The possible giant would also affect the search for smaller rocky planets. Its gravity could either disturb or permit stable orbits depending on its mass, path, and distance from the star. If the giant follows a fairly circular and stable orbit, it may occupy one region while leaving others dynamically calm. If its orbit is more elongated, it could sweep through a wider range of distances and reduce the places where small planets could remain stable over billions of years. The difference is not minor. A gas giant on a gentle path and a gas giant on a stretched path can create very different planetary systems. This is why confirming the candidate would not end the investigation. It would begin a more detailed one. Astronomers would need to determine the orbit, estimate the mass, and understand how its motion relates to the stable zones around Alpha Centauri A. Only then could its effect on possible smaller worlds be judged. The presence of Alpha Centauri B makes this question more complex. Any planet around Alpha Centauri A already exists within the gravitational reach of the companion star. The stable region around Alpha Centauri A is limited by the binary orbit, and the outer parts of any planetary system cannot extend freely as they do around a single star. A giant planet near the habitable zone would therefore be positioned inside a system where two levels of gravity matter at once. The star it orbits controls its immediate path, while Alpha Centauri B shapes the broader boundary of stability. If the candidate is real, It would have survived in this environment for a long time. That survival would itself be informative. It would suggest either that the planet formed within a truncated disk around Alpha Centauri A, or that it formed elsewhere in the disk and migrated into a more stable location, or that the early system went through interactions that left this object in its present orbit. None of these possibilities can be chosen without more evidence, but each would carry information about planet formation in binary systems. The question of moons naturally follows, but it also requires restraint. Gas giants in the solar system have large moon systems, and some of those moons are scientifically important because they contain ice, oceans, or active geology. A giant around Alpha Centauri A could in principle have moons, and if the planet lies in a region receiving moderate starlight, the idea attracts interest. Yet current observations cannot show such moons. Webb's candidate is not even confirmed as a planet, and any moons would be far smaller and fainter than the giant itself. Their existence would be speculation layered above an already uncertain detection. The careful conclusion is that a giant planet could provide environments and gravitational settings that future science would want to examine, but there is no evidence yet for moons, surfaces, oceans, or life. The candidate's importance does not require those additions. It is significant enough as a possible large planet around the nearest solar-type star. If confirmed, the planet would also help calibrate direct imaging of mature planetary systems. Many planets photographed directly are young and hot, still glowing strongly from their formation, or located far from their stars where contrast is easier. A colder giant closer to a mature sun-like star is a more demanding target, and a more relevant comparison to the outer parts of familiar planetary systems. Alpha Centauri A's nearness makes the case especially valuable, because a confirmed planet there could be followed over time with unusual precision. Its orbit could be mapped more fully than those of many distant candidates. Its brightness at different wavelengths could be measured. Changes in position could reveal how it moves inside the binary environment. Over time, its presence might help infer the structure of surrounding debris or constrain where smaller planets could remain. The discovery would not be a single point in a catalogue. It would become a nearby laboratory for studying how giant planets behave around solar-type stars in binary systems. The possible planet therefore shifts the meaning of the habitable zone without turning it into a simple promise. The region around Alpha Centauri A, where temperatures could be moderate, is important because smaller rocky planets there would be of extraordinary interest. A gas giant in or near that same region would be important for a different reason. It would occupy gravitational space that smaller worlds might otherwise use, or it might mark the edge of stable zones where smaller worlds could still exist. It might have shaped the delivery of icy material or the clearing of debris. It might indicate that planet formation around Alpha Centauri A was robust enough to make large bodies despite the companion star. These are not conclusions yet. They are the kinds of questions a confirmed giant would make unavoidable. For now, the source remains unconfirmed, and the language must remain cautious. Webb may have seen a cold giant in a region of unusual interest, or it may have recorded dust or an artifact that only resembles one. But if the planetary interpretation survives, the result would not be disappointing because it is not Earth. It would be revealing because it is large, nearby, and placed where its gravity would matter. The first confirmed planet around Alpha Centauri A, if this candidate becomes that planet, would not be a second home. It would be a sign that the nearest solar-type star has a real planetary architecture, one that may have been shaping unseen space for billions of years before the faint infrared point finally reached the edge of detection. Alpha Centauri A cannot be understood as a lonely copy of the Sun. Any planet around it must belong to a system shaped by the presence of Alpha Centauri B. a second substantial star moving through the same gravitational environment. This companion is not close enough to strip all possibility away, but it is close enough to matter at every stage of the story. It would have affected the original disk of gas and dust from which planets formed. It would have influenced which orbits remained stable over long periods. It would still place limits on how far planets around Alpha Centauri A can safely travel before the companion's pull becomes too disruptive. That makes the possible Webb candidate more than a faint object near a bright star. If it is a giant planet, it is also evidence of endurance inside a binary system, where the architecture of planets has to fit between two moving sources of gravity. Planet formation begins in a disk around a young star, where small grains collide, stick, break, gather again, and eventually build larger bodies if conditions allow. Around a single star, that disk can extend outward in a broad and relatively simple way, though even the solar system shows that the process is far from gentle. Around one star in a binary, the disk is more limited. The companion star can pull on its outer regions and prevent material from remaining stable at large distances. The disk may be truncated, meaning its outer part is cut off or stirred strongly enough that planet formation there becomes harder. The gas and dust may also be warmer, more disturbed, and less evenly arranged than in a single star system. This does not prevent planets from forming, because many binary systems are known to contain planets, but it changes the conditions. A planet around Alpha Centauri A would have formed in a neighborhood where the second star was part of the physical environment from the beginning. A giant planet is especially informative because it is not easy to build. It requires a solid core or some other concentration of material to gather enough gas before the young disk disappears. The timing is limited. Gas in planet-forming disks does not last indefinitely, so a giant planet must assemble while the raw material is still present. If Alpha Centauri A hosts a Saturn-like or Jupiter-like planet, then its early disk must have been able to create or preserve the conditions needed for substantial growth. That would be significant in a system where Alpha Centauri B may have shortened the outer disk and stirred the region in which planet building occurred. The planet would show that the binary environment did not stop large-scale planetary formation, at least not completely. It would also raise a question about where the giant formed. It may have formed near its present orbit, or it may have formed farther out and later moved inward, or it may have been shifted by interactions with other bodies that are now gone or still hidden. Migration is common in modern planet formation theory. Planets do not always remain where they first assemble. A young giant can exchange angular momentum with the surrounding gas disk and move inward or outward. Later, after the gas is gone, gravitational interactions with other planets can also alter orbits. In a binary system, the companion star adds another long-term influence. It can slowly change the shape and orientation of planetary orbits, especially if those orbits are wide or tilted. If the possible Alpha Centauri A planet has an elongated path, that shape may preserve information about earlier interactions. It could reflect the influence of the companion star, past encounters with other planets, or formation inside a disk that was never perfectly calm. The current orbit, if confirmed, would therefore not be just a line around the star. It would be a record of what the system has survived. Stability is the next essential question. A planet can exist around one member of a binary only within a region where the pull of its own star remains dominant enough over time. Too close to Alpha Centauri A, the planet is safely bound to that star, though it may face other complications depending on its neighbours. Too far out, Alpha Centauri B's influence becomes stronger and can make the orbit unstable. The exact boundary depends on the masses of the stars, their separation, the shape of their binary orbit, and the shape of the planet's orbit. Alpha Centauri A and B do not remain at one fixed distance from each other. Their own orbit is elongated. so the gravitational environment changes as they move closer together and farther apart. A planet that is stable during one part of the binary cycle must remain stable across many cycles, not just over a few years of observation. For a system that is billions of years old, survival is a strong requirement. If the Webb candidate is real, its orbit must lie within that allowed region around Alpha Centauri A. This is why orbital modelling must include more than the positions where the source appeared and vanished. It has to ask whether the object could remain bound over long times while Alpha Centauri B repeatedly passes through its binary path. Some possible orbits may match the observed points in the short term but fail as long-term solutions. Others may be dynamically safer, but less able to explain the detections and non-detections. The best surviving possibilities must satisfy both demands. They must connect the evidence, and they must make sense inside the binary. This is one reason the candidate cannot be interpreted in isolation. A faint point near a single star might be judged mainly by brightness, position, and motion. A faint point near Alpha Centauri must also be judged by whether the system itself would allow such a body to remain there. The result, if confirmed, could change how the nearest Sun-like pair is used as a comparison with the solar system. The Sun has no stellar companion shaping the edges of the planetary region. Its planets orbit within a single dominant gravitational field, with interactions among the planets themselves providing much of the later complexity. Alpha Centauri A would be different. Its planets, if present, must fit inside a smaller and more constrained stable zone. The companion star does not need to pass close to the planet to matter. Over long periods, repeated gravitational influence can accumulate. A giant planet that survives there would show that planetary systems can remain coherent, even in a setting where a second star sets the outer boundary. It would also show that the absence of confirmed planets around Alpha Centauri A has not meant an absence of formation. It may have meant that the existing architecture is hard to see. A giant planet in such a system could also affect the prospects for smaller worlds. If its orbit is stable and not too disruptive, there may be regions closer to Alpha Centauri A where rocky planets could exist without being strongly disturbed. If its orbit is more eccentric, it could cross or influence a wider range of distances, reducing the available stable space for smaller planets in the temperate region. The difference would matter greatly for future searches, but it cannot be judged without confirmation and a better orbit. A giant planet does not automatically rule out smaller worlds, and it does not automatically protect them. Its effect depends on mass, distance, orbital shape, and the arrangement of any other bodies. The binary companion adds another layer of constraints. Together, the two stars and the possible giant would define a gravitational framework in which hidden smaller planets would either find long-term stability or be removed over time. This is why the discovery of a giant would not be the end of the Alpha Centauri question. It would make the question more specific. The system would no longer be discussed as a blank nearby target. It would become a place where one large body must be fitted into a binary environment, and where the consequences for unseen planets could be calculated with much greater care. Future observations would then look not only for the candidate itself, but for the structure implied by its survival. Debris patterns, additional faint sources, small dynamical signals, and stable orbital zones would all become part of the same investigation. The possible planet would serve as the first known piece of a system whose full layout might remain difficult to complete. Alpha Centauri B therefore changes the meaning of the Webb candidate before the candidate is even confirmed. It turns a possible detection into a problem about formation and survival. A planet around Alpha Centauri A would not simply be another object added to a catalogue. It would be a body that either formed under the influence of a companion star or moved into a stable orbit after early changes in the system. It would have endured the repeated gravitational pattern of the binary for a very long time. Its present position, if real, would carry information about the limits of planet formation around close Sun-like pairs. The nearest solar-type star would remain familiar in temperature and light, but less familiar in architecture. It would show that the local stellar neighborhood may contain planetary systems shaped by forces absent from the solar system, and that the first confirmed world around Alpha Centauri A, if this source becomes one, may tell its most important story not through habitability, but through the fact that it survived between two stars. The Webb candidate matters partly because of what it may be, but it matters just as much because of what it leaves unseen. If the faint source near Alpha Centauri A is a planet, it is probably large enough and warm enough in the mid-infrared to rise above the limits of the observation for a short time. That would make it detectable under favourable geometry, while smaller bodies in the same system could remain completely beyond reach. This is an important point because the public meaning of Alpha Centauri often centres on the hope for rocky worlds. A gas giant candidate does not answer that hope directly. It shows, at most, that a large planetary body may exist around the nearest solar-type star. It does not show whether smaller planets are present, whether any of them are rocky, or whether any orbit in regions where surface water could be possible. Webb may have opened a narrow window, but the window is not wide enough to reveal the whole system. The limits begin with contrast. A rocky planet near Alpha Centauri. A would be much fainter than a giant planet in mid-infrared light. Its smaller size gives it less area to emit heat. Its temperature may make it glow most strongly at wavelengths that are still difficult to separate from the star and from instrumental background. Even if such a planet were in a temperate orbit, its signal would be extremely weak beside Alpha Centauri A. The star is close, but closeness does not remove the difference between stellar light and planetary emission. The practical question is not whether a rocky world exists in a region that can be imagined. The practical question is whether current instruments can isolate its light from the glare. For Webb, the answer is likely no for an Earth-sized planet around Alpha Centauri A. The telescope can push into a difficult range of sensitivity, but it was not designed as a full census machine for small nearby terrestrial planets around bright sun-like stars. That limitation is not a failure of Webb. It is a reminder of how demanding the task is. Webb was built to study the universe in infrared light across many kinds of targets, from early galaxies to star-forming regions to exoplanet atmospheres. Its strength is broad and powerful, but the direct imaging of small rocky planets near bright stars requires a level of contrast and control that remains beyond its ordinary reach. A telescope must suppress the star so deeply that the remaining light does not drown the planet. It must also distinguish the planet from dust, detector effects, and residual optical patterns. For a giant planet, this is already difficult. For a rocky world, it becomes much harder. Around Alpha Centauri A, the problem is sharpened by the nearby companion star, the binary orbit, and the small apparent separations involved. The result is a system where the largest objects may begin to appear while smaller objects remain hidden. This creates a careful distinction between absence and non-detection. Alpha Centauri A has no confirmed planets, but that does not mean it has no planets. It means the evidence has not reached confirmation. Smaller worlds could exist below the current detection threshold. They could orbit closer to the star, where glare is stronger, or in parts of the system where their signals do not produce transits from Earth's point of view. They could be too low in mass to create radial velocity signals that can be separated cleanly from stellar activity and binary motion. They could be stable for billions of years and still remain unseen. This is not an argument that such worlds must exist. It is an argument that the current lack of confirmation should not be mistaken for a complete map. The nearest solar-type star may still contain planetary bodies that present instruments cannot reveal. A useful way to understand this is to consider the solar system from the outside. While keeping the comparison limited, if observers near Alpha Centauri studied the Sun with technology similar to ours, they would find the Sun bright and easy to measure, but the planets would not all be equally visible. Jupiter would be the strongest planetary influence because of its mass and size. Saturn might also be detectable under favourable conditions. Earth would be far more difficult. It is small, close to a bright star, and modest in its thermal output compared with a giant planet. Venus and Mars would also be challenging in direct imaging. The fact that Earth contains oceans, continents, and a complex biosphere would not make it easy to see from 4 light-years away. The lesson is simple. The most scientifically meaningful worlds are not always the easiest ones to detect. A nearby planetary system can look sparse because instruments are sensitive mainly to its largest members. This has consequences for interpreting the Webb source. If the candidate is confirmed, it may become the first known planet around Alpha Centauri A, but it would not complete the inventory. It would more likely provide a starting point. Its orbit could define regions where smaller planets are more or less likely to remain stable. Its gravity could influence the possible placement of rocky worlds. If it has a nearly circular orbit, it may leave some regions comparatively undisturbed. If its orbit is elongated, it may reduce the stable space available to small bodies in nearby zones. Either case would help narrow the search, but neither would reveal hidden planets by itself. A confirmed giant would be a major clue about the architecture, not the whole architecture. It would tell astronomers where to look more carefully and where stability calculations become most important. The opposite outcome also leaves the small planet question open. If the Webb source turns out to be dust or an artifact, Alpha Centauri A would still not be proven empty. The failed candidate would show how hard it is to search near the star, but it would not rule out smaller worlds. It might even indicate that the system contains dust or debris, which could point to unseen small bodies grinding together over long times. Dust can be created by collisions among asteroids and comet-like objects, and those objects are themselves part of planetary system structure. A dust explanation would not satisfy the search for a planet, but it would still suggest that the environment around Alpha Centauri A is not necessarily inactive. The absence of a confirmed giant would therefore not return the system to complete simplicity. It would only remove one possible piece. The smaller planet problem also matters because of how exoplanet statistics have changed expectations. Across the galaxy, small planets are common. Many stars host planets with sizes between Earth and Neptune, and compact systems of smaller worlds appear frequently in survey results. This broad knowledge does not prove that Alpha Centauri A has such planets, because each system has its own formation history. The binary nature of Alpha Centauri may alter the outcome. Still, the galaxy has shown that planet formation is efficient, and it would be premature to treat the nearest solar-type star as empty simply because its planets have not yet crossed our instruments clearly enough. The question remains open in a scientifically meaningful way. It is not driven only by hope. It is driven by the combination of common planetary formation elsewhere and severe observing limits here. Future instruments are being developed to address this gap, but the gap remains real for now. Extremely large ground-based telescopes may improve resolution and sensitivity in infrared light. New coronagraph technologies may reduce stellar glare more effectively. Space missions designed specifically to image Earth-like planets around nearby stars may eventually search the region around Alpha Centauri A with a more suitable level of contrast. These future efforts would not merely take sharper pictures. They would try to measure the system at a different scale, where smaller planets and fainter dust structures become accessible. That is the step needed to move from a possible giant planet to a more complete understanding of the nearest Sun-like system. Until then, the system must be discussed with careful incompleteness. Webb has shown how close modern astronomy can come to detecting a faint object near Alpha Centauri A, but it has also shown the remaining boundary. The telescope may have glimpsed the kind of planet that is large enough to appear at the current edge of visibility. Below that edge could be smaller worlds, debris, or empty regions shaped by gravity. None of these possibilities can be chosen by assumption. The evidence has to grow through repeated observation, improved contrast, and careful modelling. The nearest solar-type star is not fully known because it is nearby, and it is not empty because confirmation is missing. It is a system still partly hidden by brightness, geometry, and instrumental limits. What Webb cannot see may be as important as what it may have seen, because the unseen part is where the most familiar kinds of planets would probably remain. A planet is not the only kind of object that can create faint infrared structure near a star. Around Alpha Centauri A, dust remains one of the important alternatives because dust can glow, gather unevenly, and appear in processed images as something more compact than it truly is. This does not make dust a dull explanation. In planetary systems, dust is evidence of activity. It can come from collisions among asteroids, fragments released by comet-like bodies, or the steady grinding down of material left over from planet formation. Small grains absorb starlight and re-radiate energy at infrared wavelengths, which places them in the same observational range used to search for cool planets. A telescope trying to find a giant world by heat must therefore distinguish between a single body and a loose population of warm particles. Near a bright star, where the image has already been shaped by a coronagraph and by careful subtraction of glare, that distinction can become difficult. The possible Webb source is interesting partly because it resembles what a cold giant planet might look like, but a dust feature cannot be dismissed without further evidence. A debris disk or dust cloud around Alpha Centauri A would have a different physical meaning from a planet. A planet is a bound body with a defined mass, radius, and orbit. Dust is a collection of grains, each one small, moving under gravity but also affected by radiation pressure, collisions, and the slow drag produced by interaction with starlight. A planet can be predicted as a single moving source. Dust may be spread into a belt, a broad cloud, or a clump shaped by larger unseen bodies. If an image shows one compact area of infrared emission, it may be because a planet is present, or because a region of dust is brighter than its surroundings, or because the processing has emphasized part of a wider structure. This is why the same observation can lead to very different interpretations. The faint point near Alpha Centauri. It may be a world. It may also be a sign that the space around the star contains small bodies colliding and producing warm debris. Neither answer would leave the system empty, but they would point to different kinds of architecture. Dust is especially relevant because many mature stars contain debris left behind after the main era of planet formation. The solar system has its own faint dust population. Some of it lies along the plane of the planets and comes from comets and asteroid collisions. From inside the solar system, this material can sometimes be observed as zodiacal light under dark skies. Around other stars, similar material is called exozodiacal dust. It is hard to study because it is faint and close to the star, but it matters greatly for direct imaging. Dust can create a background glow that interferes with the detection of planets. It can also reveal belts of material that planets may be shaping. If Alpha Centauri A has exozodiacal dust in the region where Webb saw the source, then the observation might not be a failed planet discovery. It could be an early measurement of the system's debris environment. That would still be important, because debris often points toward unseen parent bodies. Fine dust cannot last forever without being replenished. Radiation and collisions remove it over time, so a continuing dust signal may imply a reservoir of larger objects feeding it. The difficulty is that dust does not always present itself as a smooth glow. It can be structured by gravity. A planet can trap dust in preferred orbital locations, clear gaps, or create asymmetries in a debris belt. Collisions can also produce temporary enhancements if two larger bodies break apart. In a binary system, the companion star may influence how dust is distributed over long times. Alpha Centauri B may stir or limit material around Alpha Centauri A in ways that differ from a single star system. This means that a dust explanation does not remove planetary questions. It may actually lead back to them. If the source is not a planet but dust, astronomers would still ask what shaped the dust, where the parent bodies are, and whether unseen planets are influencing the pattern. A dust feature can therefore be both a false world and a real clue. It may fail to be the object first hoped for while still revealing that the system contains structure below the level of direct planetary confirmation. Separating dust from a planet requires time, wavelength, and motion. Time matters because a planet should follow a predictable orbit as a compact source. If the Webb candidate is a planet, it should reappear at positions allowed by the models when its apparent separation from Alpha Centauri A becomes favourable. Dust may change more diffusely. A persistent belt may appear extended rather than point-like when observed with enough sensitivity. A temporary clump may fade, spread, or shift in a way that does not match a single orbiting body. Wavelength matters because dust and planets can have different infrared colours. A planet's emission depends on its temperature and atmosphere, while dust emission depends on grain size, composition, distance from the star, and heating. Observing at more than one wavelength can help distinguish these possibilities, though the measurements are difficult near such a bright star. Motion matters because a planet's path is constrained by a single orbit. While dust may represent many small particles moving together only loosely, none of these tests is simple, but together they provide a way forward. Instrumental effects remain a separate concern. A false source created by the telescope or processing may resemble either a planet or dust in one observation. This is why repeated detections are essential. If a feature appears in the same way when the observing geometry changes, or if it moves in a pattern tied to the star rather than the detector, its physical case improves. If it appears only under one processing approach or one observing setup, the case weakens. Around Alpha Centauri A, the problem is intensified by the strength of the starlight and by Alpha Centauri B's contribution to the field. The residual image after starlight suppression is not a blank background. It is a complicated surface of remaining light. A small feature on that surface can be meaningful, but it can also be deceptive. The scientific task is to avoid assigning physical meaning too quickly, while still recognizing when a signal deserves follow-up. The dust possibility also changes how the Alpha Centauri system might be imagined. A clean planetary system would consist of stable planets in ordered paths, with relatively little leftover material. A dusty system is more active. It may contain belts of small bodies, recent collisions, or gravitational stirring that keeps material in motion. If warm dust is present around Alpha Centauri A, then the system may have a population of asteroids or comet-like objects that has not yet been mapped. This would be especially relevant for future searches for smaller planets, because dust can interfere with attempts to image rocky worlds directly. A bright enough dust cloud near the star could raise the background against which an Earth-sized planet would have to be detected. In that sense, dust is not merely an alternative explanation for the Webb point. It is also part of the observational environment that future missions must understand. before they can search for fainter worlds with confidence. There is a careful balance in this interpretation. Calling the source dust should not be used as a way to make the result unimportant. Calling it a planet should not be used before the evidence is strong enough. Both possibilities lead to serious science. A confirmed planet would reveal a large body around the nearest solar-type star and would immediately become a central target for orbital and atmospheric study. A confirmed dust feature would reveal material in the same difficult region and would help define the conditions under which future planet searches must operate. It could point toward unseen belts, ongoing collisions, or the gravitational influence of bodies too faint to see. The difference is not between discovery and nothing. It is between different kinds of discovery, one more direct and one more environmental. The present evidence cannot yet choose between them. The faint source appeared once, failed to return in later Webb observations, and remains compatible with more than one explanation. The next observations must test whether it behaves like a compact body or like something less fixed. If it returns along a predicted path, the planet case strengthens. If it does not, and if broader infrared structure appears instead, dust may become the better interpretation. If neither pattern holds, the source may eventually be understood as an artifact of an extremely difficult observation. Alpha Centauri A has therefore become a test not only of whether a nearby planet can be seen, but of whether astronomy can distinguish a world from the material and light around it. That test is essential because future searches for smaller planets will face the same confusion in a more severe form. The system next door may contain a giant planet, a debris structure, both, or neither. What Webb has shown is that the region around Alpha Centauri A is no longer only an empty place in the catalogue. It is a field of possible signals where planet, dust, and instrument must be separated with patience before the nearest solar-type star can be understood. The next stage of the Alpha Centauri A candidate is not a matter of preference or expectation. It is a matter of timing, position, and repeated measurement. Webb has already provided the first difficult part of the record. A faint source appeared near the star in August 2024, then was not recovered in later observations during early 2025. That sequence is incomplete, but it is not shapeless. It gives astronomers a position where the source was seen, dates when it was not seen, and a range of possible orbits that can explain both facts if the source is a planet. The work now moves from discovery language into prediction. A real planet must continue along a gravitational path. It cannot choose a convenient place to appear, and it cannot return at random. If the candidate is a body bound to Alpha Centauri A, then future observation should eventually find it at a location allowed by orbital models, outside the region where the coronagraph is most strongly limited by glare. This is the strongest test because it asks the source to behave like matter rather than like a feature of one image. A single faint point can be ambiguous. A returning point in the right place becomes much harder to dismiss. The future observations must be planned around the geometry of the system. Alpha Centauri A is bright. Alpha Centauri B contributes its own light, and the possible planet would move through a small angular region close to the star from Earth's point of view. There will be times when the candidate, if real, lies too near the star's apparent position for Webb to separate it from residual glare. There may be other times when the same object is far enough away in projection to become detectable again. This means that not every follow-up attempt has the same value. An observation taken at an unfavourable point in the orbit could fail even if the planet exists. A better timed observation can test the surviving orbital paths more directly. The search, therefore, becomes more patient and more exact. Instead of asking only whether something is there, astronomers ask when the object should be visible, where it should appear, and whether the predicted position can be checked with enough contrast to matter. If the source returns according to one of the allowed paths, the interpretation will change quickly. The candidate would no longer be only a faint source beside a difficult star. It would have demonstrated motion consistent with an orbit around Alpha Centauri A. That would not immediately reveal every property of the planet, but it would establish the most important fact: the source belongs to the system. From there, the work would become more detailed. The orbit would be refined as additional points were added. Its size, shape, and tilt would become clearer. Its brightness in different infrared wavelengths could help estimate temperature and atmospheric properties. Though model uncertainty would remain, its effect on possible smaller planets could be studied through stability calculations. Its relationship with Alpha Centauri B would become part of the evidence for how planets form and endure in binary systems. A confirmed world would turn Alpha Centauri A from a star with no known planets into a nearby planetary laboratory, and because the system is so close, that laboratory would remain accessible to repeated study in a way that many distant systems are not. If the source does not return when models predict it should be visible, the conclusion will move in another direction. The planet interpretation would weaken, perhaps strongly, depending on how complete the future observations are. Scientists would then revisit alternatives with more weight. Dust could become a better explanation if broader or changing infrared emission is found. An instrumental artifact could become more likely if no physical pattern survives repeated attempts. A background or local object would be reconsidered according to motion and position. This would not make the original observation meaningless. It would teach how faint structures behave near one of the most demanding bright stars Webb has studied with this method. Failed candidates are part of the way direct imaging improves. They show where residual starlight can imitate sources, where processing can mislead, and where future instruments must be more careful. Around Alpha Centauri A, even a non-confirmation would be valuable, because the target is a preview of the challenge future telescopes will face when looking for smaller and fainter worlds around nearby sun-like stars. The larger meaning of the candidate lies in how it changes the status of the nearest solar type system. Before the Webb observation, Alpha Centauri A and B were famous, close, and still without confirmed planets. After the observation, that statement remains technically true, but the scientific situation is not the same. There is now a specific candidate near Alpha Centauri A, a possible connection to an older ground-based signal, and a set of orbital predictions that can be tested. The system is no longer only a blank entry in the exoplanet catalogue. It is a nearby unresolved case with defined evidence and defined uncertainties. That shift matters. In science, progress does not always arrive as confirmation. Sometimes it arrives when a vague absence becomes a precise question. Alpha Centauri A now has such a question. Is the faint infrared source a giant planet moving in and out of visibility, a dust feature shaped by hidden structure, or a false signal produced by the difficult act of looking beside a bright star? The answer will come not from a stronger story, but from a stronger pattern in the data. This also changes how the nearer stars are understood in a broader sense. Closeness can create a false expectation of simplicity. A star only a little more than 4 light-years away feels like part of the immediate neighbourhood, and a neighbour can seem almost known because it has a name, a position, and a long history in the human sky. But astronomical knowledge depends on more than distance. It depends on contrast, alignment, wavelength, instrument design, and time. A nearby planet can remain unseen if it is too close to a bright star in the image. A small rocky world can remain hidden, even if the star itself is one of the best studied in the sky. A giant planet can be suspected for years before enough evidence exists to confirm it. Alpha Centauri has become a clear example of this principle. The nearest system beyond the Sun is not transparent. It is close enough to study carefully, but not close enough to remove the deepest observational limits. Future missions may eventually change the scale of the problem. More advanced coronagraphs could suppress starlight more cleanly. Larger ground-based telescopes could sharpen infrared measurements. Space observatories designed specifically to image nearby Earth-sized planets could search for smaller worlds that Webb cannot see directly. Alpha Centauri would be an obvious target for all of them, not only because it is close, but because Webb has shown that the region around Alpha Centauri A may contain meaningful structure at the edge of current detection. A confirmed giant planet would guide those searches by defining part of the system's architecture. A confirmed dust structure would guide them by defining the background through which fainter planets must be detected. Even an artifact would guide them by showing how carefully instruments must control glare around this particular star. Each outcome narrows the uncertainty in a different way. The final position of the present story is therefore deliberately open. The responsible account does not end by declaring a planet, because the evidence has not reached that level. It also does not end by dismissing the candidate, because the later non-detections can still fit some plausible orbital paths. The source remains a scientific maybe with unusually high importance. It may be the first directly imaged planet around the nearest solar-type star. It may be warm debris or dust revealing hidden small bodies. It may be a lesson in the difficulty of separating real planetary light from the complex remains of stellar glare. For Alpha Centauri A, all three possibilities are meaningful because each one would explain why the system has resisted easy interpretation for so long. What Webb has changed is not the final inventory of planets, but the sharpness of the search. The nearest sun-like star is no longer only a familiar point with an empty planetary record. It is a system under active test, with a faint source that must either return according to gravity or fade into the archive of difficult signals. Until that test is complete, Alpha Centauri remains both close and unresolved, a nearby frontier where the next answer depends on whether a small point of infrared light can be found again in the right place. The Alpha Centauri story rests, for now, in a careful pause. A nearby star has offered a faint signal, not strong enough to become a confirmed world, but too specific to be ignored. Around Alpha Centauri A, the question has narrowed from a broad hope into a precise test of light, motion, and patience. If the source is a planet, it must continue along its orbit, returning only when geometry allows it to separate from the glare. If it is dust, the system may still be active with small bodies, collisions, and material too faint to map in detail. If it is an artifact, it will still have taught astronomy something valuable about the difficulty of looking beside a bright star that is almost, but not quite, like the Sun. In every outcome, the nearest solar-type neighbour becomes less simple and more real. Its closeness no longer guarantees understanding. Its brightness no longer feels like pure advantage. The system stands as a reminder that discovery often begins with restraint, with a small uncertainty made sharper by better instruments and repeated observation. Webb has not closed the Alpha Centauri question. It has given it clearer edges. Somewhere in the data there may be the first sign of a large planet moving through that nearby system, or there may be only the trace of dust and glare shaped into a temporary point. The difference will be decided slowly, by future measurements, and by the steady discipline of gravity. Until then, Alpha Centauri remains close, bright, and unresolved. A familiar name in the sky still holding back part of its structure. The nearer stars have not lost their mystery by being nearby. They have become a quieter kind of frontier, one where the unknown begins not in distant galaxies, but just beyond the reach of the sun.